Hello everyone, welcome to the class. Today we will start the last topic of module 12, which is introduction to lasers. Now the laser word is an acronym for a big sentence which is light amplification by stimulated emission of radiation. Now if you pick the first character of each word, then it will form laser. You see that L is coming from here, A is coming from here, S is coming from here, E is coming from here and R from here. Okay. The light is being amplified through a process called stimulated emission of radiation, and in this process whatever output we receive we call it laser. Lasers are the light source which have certain properties, and these properties are that they are highly monochromatic, they are highly coherent and they are highly directional. Monochromatic means the bandwidth of a laser is very small. Ideally it should be one wavelength or one frequency, but this is not possible in the reality. Yeah, and therefore all the lasers have certain bandwidth, and therefore the light which is emitted by a laser, it has least bandwidth, and therefore we call it almost monochromatic light. The second point is that laser light is highly coherent, which we have already studied the word, we know what coherent is. Yeah, the light emitted by laser, they maintain the constant phase relationship, and this is why we call them coherent light. And they are highly directional, they do not get diverged too early, they propagate collimated through a long distance. Okay. And the first laser, which is called ruby laser, was demonstrated in 1960 by Theodore Mammon, and this demonstration revolutionized the field of optics. Okay. And then right after the invention of the laser, we saw that there appeared a huge application of this, but before that we will go through the basics of laser. Now here we will talk about light matter interaction. At the root of light matter interaction, we have electromagnetic radiation absorption and electromagnetic radiation emission by an atom. Whenever we say atom, then the energy level diagram of an atom should appear in our mind, which was initially proposed by Rutherford and then later corrected by Bohr, and then several other models appear. Now since atom is a discrete quantity, and if it is isolated, then it will have a discrete number of energy levels. Let us pick two energy levels out of it, okay, and let us name them as energy level 1 and energy level 2. The corresponding energies are represented by E1 and E2 respectively. Now say there is an electron in the lower energy state. Now if we launch a photon of appropriate energy, by the word appropriate energy I mean is following: the energy which is h cross omega or h nu, it must be equal to the energy difference between the two levels. Okay. If a photon of this energy is launched into this atom, then there is a finite probability that this electron from energy level 1 may go to energy level 2, may transit to energy level 2, and in this process the incident photon is absorbed by the transiting electron or the atom, and this process is called absorption. Similarly, if the electron is in the upper energy state, then after residing there for a while, it may go down to the ground state or the first state, and during this process it emit a photon of energy h nu or h cross omega. This process is called emission. Now in 1917, it was Einstein who predicted that an atom can emit radiation by two ways. Okay, although there was only one way of absorbing the photon or absorbing the radiation, that we named as absorption. There are two ways of emission as proposed by Einstein, and these two ways are called spontaneous emission and stimulated emission. In spontaneous emission, the electron from the upper energy state make downward transition with an emission of photon of appropriate energy. Okay. Now, in this process we see that as soon as the electron goes down, a photon get emitted, and this happens spontaneously without the requirement of any external perturbation, and this is why the phenomena is called spontaneous emission. Second equivalent phenomena is stimulated emission. Herein the electron from the upper level, it makes downward transition in presence of an external stimuli, which is photon here. Okay. Now, in this case, suppose the electron is here in the higher energy state, and if appropriate energy photon is launched, then the electron go to the lower energy state along with an emission of a photon of appropriate energy. Now, this emission happened in presence of an external stimuli or an external photon, and therefore, this process is called stimulated emission. Okay, it requires an external field or external photon or external radiation. Now, this is the difference between the two. Yeah, here we do not require any external stimuli, and here we require. Now, consider two energy levels, the energy level 1 and energy level 2. The energies of these levels are designated by E1 and E2 respectively, and the carrier densities, that is number of electrons or number of atoms per unit volume present in energy levels E1 and E2 are respectively given by N1 and N2. Okay. As is clear from the figure, the energy difference between the two level is E2 minus E1. Okay. And there are certain distribution of charge carrier or electrons between these two energy levels. Now, if radiation at frequency corresponding to the energy difference E2 minus E1 falls on the atomic system, then it can interact in the following three ways. In the first case, the ground state atom is reached in the excited state by absorbing the radiation, and which we call absorption. The rate of transition from level 1 to level 2, it will depend upon the number of atoms present in the ground level or level 1, and it will also depend upon the energy density of the radiation at frequency omega, and this omega is related to E2 minus E1 through this relation. Okay. I repeat, if we launch a radiation on this two level system, then the atoms from the ground state or the electrons from the ground state will absorb this radiation and move to the upper level. Now, this upper level transition or this phenomena of absorption will depend upon the carrier density or the number of atoms present in the lower level and on the energy density of radiation at frequency omega. Okay. Thus, if U omega d omega represents the energy density per unit volume between frequency omega and omega plus d omega. Okay, we are considering a width in the frequency, because as I already said that the single frequency is not possible. Yeah, there is always a width associated with each emission and absorption. Therefore, U omega d omega represents the radiation per unit volume between frequencies omega and omega plus d omega in this bandwidth. Now, with this, the number of atoms undergoing absorption per unit time per unit volume from level 1 to level 2 is given by equation number 66, which says gamma 1 2, which is number of atoms undergoing absorptions per unit time per unit volume, it would be proportional to the energy density u omega and the carrier density in level 1 or density of atoms or density of electrons in level 1. And B12 is proportionality constant, it is constant of proportionality and it depends upon the energy levels E1 and E2. Okay. Now, the absorption happen in presence of the external radiation. Now, what will happen to the atoms or electrons which are in the upper level, in the level 2? Now, they will make downward transition and which is called de-excitation. Now, as we studied before, there are two processes of de-excitation, one is called stimulated emission and the second is called spontaneous emission. Okay. Now, two distinct processes are involved in the de-excitation of the atom from energy level E2 to energy level E1. In stimulated emission, the rate of transition to the lower level is proportional to the energy density of radiation at frequency omega and the number of atoms in energy level 2 or upper energy level. Therefore, the number of stimulated emission per unit time per unit volume would be given by equation number 67. Okay. Now, I repeat, in the stimulated emission the rate of transition to the lower level is proportional to the energy density of radiation at frequency omega, as well as it is proportional to the number of carriers or carrier density in energy level 2 or upper energy level, and therefore, the number of stimulated emissions per unit time per unit volume will be given by equation number 67, where B21, which is again a proportionality coefficient, it depends upon the energy level. Okay. Observe the difference between the two B coefficients which we saw. In equation 66, it is B12, it is designating transition from level 1 to level 2. Okay. And in equation 67, we have B21, which is representing transition from level 2 to level 1. Okay. Here we are talking about stimulated emission, and in the earlier equation we were talking about absorption. Now, let us talk about spontaneous emission. An atom which is in the upper energy level E2 can also make a spontaneous emission. Rate of transition here in spontaneous emission will be proportional to N2, and thus the spontaneous emission per unit time per unit volume, it would be given by equation number 68, which says that the number of atoms or the number of spontaneous emission per unit time per unit volume would be proportional to N2. Okay. Now, since spontaneous emission process does not require presence of external radiation, and therefore, in equation 68 we see that we do not have any expression of u here, as we saw this in equation number 67 and 66. Okay. Contrary to these two expressions, we do not have u in equation number 68, we have only N2 and proportionality constant, which is A21, which is a constant of spontaneous emission. Now, at thermal equilibrium, when the number of upward transition is equal to number of downward transition, the 1 to 2 transition, means this upward transition, would be equal to 2 to 1 transition. This is the downward transition. Okay. This is absorption, and here we are having this is spontaneous emission, and this is for stimulated emission. Now, let us solve this equation 69 for u, and after a bit of algebra we get an expression of u, which is energy density, and we see here that in the denominator we have N1 by N2 term, but we know from the Boltzmann law the ratio of the equilibrium populations of levels 1 and 2 at temperature T is given by this expression. which says N1 by N2 is equal to e to the power E2 minus E1 by kBT, and since E2 minus E1 is equal to h cross omega, this expression would be equal to e to the power h cross omega upon kBT. Therefore, N1 by N2 in equation 70 can be replaced by e to the power h cross omega by kBT, where where kB is nothing but Boltzmann constant, the famous Boltzmann constant, and the modified expression for energy density U hence given by equation number 72. But we also have a Planck's formulation for the energy density, and according to Planck's law, the radiation energy density per unit frequency interval is given by equation number 73. Now, we will compare equation number 72 and 73, because on the left hand side we have the same term u omega. In this expression, c is speed of light and in vacuum or in free space, and n naught is the refractive index of the medium. Now, if you compare equation number 72 and 73, then we see that B12 must be equal to B21, yeah, and let us say that this is equal to B only. Okay. Now, if you assume that B12 is equal to B21, then we can take this out of this bracket, and then we will have this term which would be equal to h cross omega cube n naught cube by pi square c cube, which is term which appears in equation number 73 here. Now, the coefficients A and B are known as Einstein's A and B coefficients. Yeah, here I have removed the subscripts 2 1 and 1 2 from A and B. Yeah, this A, capital A and capital B are known as Einstein A and B coefficients. Now, at thermal equilibrium, the ratio of the number of spontaneous to stimulated emission is given by this expression. Okay. And here what you see is that A21 N2 is the spontaneous emission and B21 N2 U is stimulated emission. The spontaneous to stimulated emission numbers is equal to e to the power h cross omega kBT minus 1. Okay, because A21 upon B21 is equal to this number, N2 from this expression will go away, and we will be left with e to the power h cross omega by kBT minus 1. Now, if in this expression in equation 68, now if you at thermal equilibrium T for large frequencies means when omega is much larger than kBT by h cross, yeah, then you see that when omega is much larger than kBT by h cross, at thermal equilibrium the spontaneous emission dominates, because this term you see that this is exponential, and if omega is much larger than kBT by h cross, then this term would be much larger than 1. Therefore, the numerator would be much larger than the denominator, and numerator here represents the number of spontaneous transition, while the denominator represents the number of stimulated transitions. Now, at thermal equilibrium for visible light where omega is much larger than kBT by h cross, spontaneous emission dominates, yeah, and hence at optical frequency light from usual light source is therefore incoherent, okay, because spontaneous emission is dominant. Therefore, at ambient temperature or at thermal equilibrium, say at T is equal to 1000 Kelvin, we always see spontaneous emission, we always see an incoherent light source. Yeah. Now, we know that in two level system the rate of upward transition, it depends upon the carrier density in lower energy state, while the rate of downward transition, it depends upon the carrier density in upper energy state. Now, if N1 is larger than N2, then the upward transition rate would be larger than the downward transition rate, or upward transition rate it would be larger than the downward transition rate. But with this a situation will arrive, because upward transition rate is larger, therefore, the number of electrons which are getting transited to the upper energy state, it would be more. The number of electron which is getting transited to the energy level 2 per unit time would be larger, therefore. Yeah, and therefore, a situation will come where this will lead to a situation where N1 would be almost equal to N2. Okay. In this situation, there would be 50-50 distributions of electrons in the two energy levels. Now, in this case, since N1 is almost equal to N2, the rate of upward transition would also be equal to the rate of downward transition. Okay. And therefore, this will lead to rate of upward transition equal to rate of downward transition. Okay. Now, since the upward transition rate is equal to downward transition, system is now in equilibrium. Okay. By anyhow we cannot invert it, or by anyhow we cannot make the upward transition rate smaller than the downward transition. Okay. And therefore, if initially N1 is larger than N2, we can never have N2 larger than N1. This will never happen. Okay. Now, the situation where N2 is larger than N1 is called a population inversion, okay, or inverted state. When N2 is larger than N1, then the number of downward transitions would be larger than number of upward transition, and in this case we will have some gain from the system. The number of absorbed photon would be smaller than the number of emitted photon, then effectively we will have some output from the two level system. But we can see from the Einstein relation that in two level system the population inversion cannot happen. Okay. Population inversion means the state in which N2 is larger than N1, or population density or carrier density in upper energy state is larger than the lower energy state. This can never be achieved in two level system, and therefore, we cannot realize laser in two level system. We will talk more about lasers, but let us stop here in this class. We will continue in the next class, and thank you for joining me.